Okay, so I actually started this last time and kind of introduced the topic. What I want to do today is, in this case, talk about a specific set of studies that actually are a decade old at this point. So actually it's not so much new data anymore in the way that science goes. But still, I think it's useful. I want you to focus on how our ability to put new instruments in orbit and on the surface of Mars that give us better data than we had in the past, allow us to ask better questions and to refine the answers that we are doing for those questions. So last time we kind of introduced the topic of valley networks. Again, what are we talking about when we're talking about valley networks? Let's go to Lizette.
Places where water, a volcano thing.
Okay, we want to interpret them maybe as places where water went, but what we actually see is what?
Like a deep valley with like branching off the sides of it, almost like a river.
So we've got, oops, let's get a pencil. We've got this basic structure that shows up in a number of locations, primarily the older parts of Mars, branching series of channels. These are obviously on modern day Mars dry, so dry branched channels. And there are a variety of ways they might have formed. They could have been cut by lava flows. They could have been cut by wind erosion. They could have been cut by a variety of things. But basically, it's pretty clear that these are water-generated structures. The big question I left you with at the end of the time last time was, are these structures being cut by water that's flowing across the surface of the ground, like we would expect with a river system where you've got rainfall being captured in some drainage basin, and that rain water flowing across the surface of the ground, eroding and forming channels, and those channels forming brooks, and those brooks forming rivers, and those rivers flowing to the sea. So that is one way that water could have cut these, and that would involve actual precipitation and water running across the surface of the ground. But another way that water could cut these is from underneath. So groundwater flowing underneath the surface of Mars could have eroded these channels from below, and these channels could have been basically eaten back up the hillside by this underground erosion. That's what's known as this groundwater sapping. Now, from an importance standpoint, why is it important to know whether these channels were formed by overground erosion versus underground sapping? Colin.
It could say a lot about what the surface of Mars was back then, and like how it, like if it was runoff, then the surface of Mars was probably more like Earth's. Or if it was sapping, it's less likely that it was like that.
Okay, so yeah, if there's runoff carving these channels, then we almost have to assume, or our interpretation would be, that back then Mars had a hydrological cycle, a water cycle, very much like that on the Earth, with rainfall and snow and rivers running to the sea and so forth. Whereas if it is sapping, if this is all groundwater that is causing this erosion from underneath, you don't really have to have a thick atmosphere. You don't have to have warm temperatures. You don't have to have Earth-like conditions for there to be enough temperature, enough warmth underground to have water running through the underground areas and cutting these channels. So fundamentally, that's why we're interested in this question. This question by itself can really tell us how Earth-like was Mars back in the day. The day being, 4 billion years ago, but back in the day. So for a long time, people had been arguing, well, we don't really have any convincing evidence of real hydrological cycles going on here. Everything we can see can be explained by this groundwater sapping, because if we look at these valley network systems as we originally, actually, when did we originally see these valley network systems? Which missions? Mariner, or which? Mariner 9, and the Viking orbiters in particular also gave us good images from orbit. These are when we first saw these valley network systems. Okay. So initial analysis of those data from Mariner 9 and from the Viking orbiter cameras showed that these valley network systems are nowhere near as branched as the kind of river systems we see here on the Earth. They're stubby, they don't have the fine scale branching that we would expect to see if, say if the Mississippi River system dried up, we would still see the remnants of it, right? As these channels. And we could tell how branched, we could tell where the Ohio River used to be, even though the Ohio River is not there anymore, and we could say, well, how many tributaries, how many branches, what kind of other stream physical geography measures we could look at, and we could say, these river systems here on the Earth tend to be branched at this level of complexity, of density of branches, of length of branches, and so forth. And when people looked at the initial images of these valley networks from Mars, they were nowhere near as complicated, as complex, as branched as what we see here on the Earth. Okay. So which of these two mechanisms, groundwater sapping or complete hydrological cycle, does that observation tend to support? Groundwater sapping, okay. We don't see in the initial images from orbit enough complexity for us to make the case that, no, this is too complex for groundwater sapping to have cut through the hillside. What we're really talking about is not having enough data essentially to support this idea of an overland flow of rainwater collecting in river basins. So this newer work, newer being about a decade old now, basically took advantage of the fact that starting in the early the late 1990s, early 20 knots, whatever you want to call them, we started sending better spacecraft to Mars with better instruments. And in particular, what they did was to rely on data coming back from the Mars Global Surveyor mission. The Mars Orbiter Laser Altimeter that provides that detailed elevation map that we've looked at a number of times with the rainbow-colored elevation data. And the Mars Orbiter camera, which is substantially better than the cameras that we were able to send back in the 70s with Mariner 9 and the Viking orbiters. Okay, so clearly our cameras have gotten a lot better. And so these researchers decided to take advantage of that new data to reanalyze how complex these structures were, to know whether or not that would argue for groundwater sapping versus overland runoff. Okay, so here's just one example. We can go through this quickly. This is the kind of, a very typical kind of valley network system you could see off of the Viking imagery. You can see the Viking imagery is somewhat low resolution. It looks a little fuzzy. You can't see a lot of fine detail. But you can definitely see these channels here with some tributaries coming off. And so, if you look at this, does not really look a lot like the Mississippi River Valley. And so this was the kind of analysis that for a long time said, we really can't argue anything beyond groundwater sapping because we don't see any data that would cause us to go beyond that. Same thing here. Here's just another example of some channels that you can recognize from the Viking imagery. And again, we've got relatively low order networks, which means there's not a lot of branching of the branches of the branches. Okay, so here we can see, this channel here doesn't have any branching at all. This one has a branch point here, but that branch itself has no evidence of further branching the way we would expect with a river system here on the Earth. Okay. Now, before I go on to the data from the Mars Global Surveyor, if you wanted to argue for overland erosion and stream order densities and so forth comparable to what we have here on the Earth, what argument could you make for why they're not showing up here in these Viking images? Sam? Maybe the camera doesn't have high enough resolution. So the branching might be there, but we're not seeing it in the Viking images. Even if we did have an Earth-like hydrological cycle in the past, carving these channels as river basins, why might those branches no longer be around?
It's been hundreds of thousands of years.
It's been billions of years.
Billions of years, thank you. It's like they could have eroded.
Okay, so over billions of years, if you took the Mississippi River basin and subjected it to a billion years of erosion, which of the channels are going to disappear the first?
The smaller ones.
The smaller, the fine ones, okay? So that was the argument back and forth. The data we see from orbit, from the Viking, doesn't really give us any reason to expect or to go beyond this groundwater sapping idea. But then the other camp could argue back, yeah, well, it's either we're not seeing them or they used to be there, but they were eroded over time. So here's what you get when you look at the same area with more recent data, with the finer resolution. There are two things going on here. First of all, the camera, the Mars Orbiter camera, does provide much higher resolution images, so it's easier to spot those small channels. And by adding in the elevation data from the laser altimeter, you can identify where channels should have run if there were a channel in this area because of the way the slope of the land is. The Viking data really looks very flat. It doesn't really give us any clue as to what's uphill and downhill. But if we've got that elevation data, I mean, clearly in this area, we've got a high elevation point here, and we're going off to a lower elevation, so we would expect these channels to drain from the high elevation to the low elevation. And so if you compare the red channel from the Viking image to the yellow channel from the more recent images of the same area, so you can see these craters here are here, so we're looking at the same area. What do you see? Comparing this to this.
It's more veiny.
More veiny. It's more branched. We have a higher density of branches. We have a higher number. The branches are more likely to have branches. So this is clearly a lot more complex structure that we can identify from the new data than were available from just analyzing the data from the Viking mission back in the 70s. Here's just another example. In this case, it's interesting that these channels that showed up as independent or isolated channels in the Viking data, when you have more complete analysis of the landscape, you can see that those channels actually are parts of a larger channel system. So again, we see a lot more branching, higher branching density, a greater stream order. The branches are more likely themselves to have branches. And if you gather into this table, you can see that, generally speaking, when you compare older data to newer data, we have from site after site after site, more complex valley network systems showing up. And so, again, this is just an example of a specific, these were actually maybe 2 or 3 papers that came out in that 2003, 2004 timeframe, where they were taking advantage of this new data to reanalyze a question that had been analyzed earlier with the Viking data, and with the better instrumentation, the more complete data, the higher resolution data, the data could be reinterpreted, and the evidence for the valley networks really being river systems is essentially much stronger than it was before we had this data. Okay. And again, why is this important that there were actually rivers on Mars?
Can you tell us a lot about what the environment of Mars was
Right.
when there was water?
Okay. Yeah, it would be important. And as I think I mentioned last time, I can't think of something that would really make Mars Earth-like more than the fact that at some point in its past, Mars had rainfall. I mean, if you could imagine a summer day on Mars with a rainstorm, that by itself makes Mars, at that point, much more Earth-like than anything we see today.
Mhm.